It was 1920. Ronald Fisher, R.A. Fisher as we know him, stumbled upon the idea of sufficiency. In this paper, as you can see on the screen, a mathematical examination of the methods of determining the accuracy of an observation by the mean error and the by the mean square error. So how did I come to know about that? So if you know Stephen M. Stigler, he is a famous statistician and historian of statistics. So in his paper he wrote, I will show you the paper, and I learned a bit about him. I also read this paper, that he stumbled upon the idea of sufficiency in 1920. And although he didn't name sufficiency under the following year, but the core idea was in this paper that he took a normal distribution and he discovered that, and he wanted to find an estimate of the normal distribution with location parameter and scale parameter. Now it's called the mean and the variance. And he wanted to find an estimate of the variance. And he found out that if we just know the variance, okay, if we just know the variance, then, and not any other thing like x bar, but if we just know the variance, not the sample mean, then we can actually find an estimate of the sigma square. We don't even need the sample mean if we just need the variance. But you can think that, yeah, sample mean is dependent upon the variance, but that's not true. You know, for a normal distribution, x bar is independent of the sample variance. We will prove that using Basu's theorem, but this is something interesting. And he told that in his work, if you can see on the screen, that the whole information with respect to sigma, the sample, you know, the population variance, this scale parameter, is summed up in the value of sigma 2 that he has obtained an estimator. So this was the starting point of sufficiency, historically. Now I will show an example, and I will start with a very basic example of the idea of sufficiency, and we will also relate it to something called graphical models that we have done. And I will just draw a picture and I will show you how it's really beautiful. So let's get started. So what I will do is that I will start with a Bernoulli process. Let me share my screen. And we'll see with the corresponding parameter, and we will see how we can reach the point of sufficiency. And you will find it really interesting. So imagine, forget about the Bernoulli process. Imagine that you're tossing coins and keeps on tossing. You keep on tossing, keep on tossing. You do it 100 times. The question is that, and you know don't know the probability of success or probability of heads. So you want to get an estimate of the probability of heads. So this you can model it as x1, the coin costs that x 100 follows Bernoulli P, and you want to know and get an estimate of P. And you know, P hat has a very good estimate. You have done the MME, you have done the MLE, and you have gone. It's also intuitively, P is the probability of success or heads. So what you count the number of heads and divide it by total number of tosses. So here it's x1 plus x2, the x 100, it counts the total number of heads, right? This is sum is binomial, so it counts the total number of heads in 100 tosses and divided by 100, that is m. So we can write it as x bar, it's m as x bar. The mean, you have done this mathematically. That's why it's a good estimate. So this is a very good estimate. Now observe that if we just know this value of the estimate and nothing else, we don't need to know just individual what they came out. Let's say it was 1, this was 0, this was 1. We don't need to know that. We just need to know the average number of the average, the average. What is the average? The average number of times heads occurred. And that will give you the entire information about P that you want to get. And that's very good information. So the information about P via the sample is just attached through X bar. That means if you have the sample here, x1, x2, xn, and you have X bar, if you know X, from that you know X bar, and from that X bar you're getting P hat, or information about P. So observe that P hat, the symbol of P hat, the information about P hat is only dependent via X bar through the sample. That means if you just know X bar, you know entire information about P. That's strong. And this is the idea of data compression in the modern days. Like you're compressing the data to a certain point, that if it's just that minimum amount if you send, that's done. In fact, in a corresponding in the electrical engineering sense, there was a great scientist called Claude Shannon, and he showed that a similar thing, that up till a certain point, if you can send a message, that's just, that's just it. For example, another way is that it's data compression is that, let's say I write that let's say I write this. You can see that once I write this, if a person writes this instead of this, you can see that maybe the closest word is that only what is right on writing maybe sufficiency. Right? That's why people use like smaller things, smaller data compressed messages in WhatsApp or whatever you use. So the sufficiency is nothing but data compression to the point that is we are only interested about the parameter P. The parameters. So we can see that if x1, x2, xn follows some distribution f of theta, theta curl maybe, a range of parameters, a set of parameters. And so the question is that what is that corresponding tx? That corresponding tx says that the data x1, x2 sample is just dependent. The parameter value is just dependent on tx. Tx can be a vector of ti is like vector of estimators. So the question is that what is this tx, this compressed data stuff, which can give the entire information about theta without knowing the sample. In case of Bernoulli P, for P, it was X bar. What's else? For Fisher, he found out for sigma square, for sigma, it was 1 by n summation x minus x bar square, the sample variance. The question is, how can you find this? How can you find this entire thing? What is the idea behind it? What is the math behind it? So in our course, the statistics full course going on, we will be learning into the depth of this. But I will share with you the mathematical modeling of this. So how can you say that a sample, if I say that, how can you understand whether a sample contains information about a parameter or not, or a distribution contains information about a parameter or not? It's all in stochastic in nature, probabilistic in nature, right? So understand this very carefully. So that's where I come to graphical models. This sample is dependent, like theta is dependent on the sample via tx. So if we know tx, if you remember, if we know tx, then in some sense, we are not adding any extra information to theta if we know xi, the sample, right? If you remember the graphical models thing, if we know, or you can think it naturally, if we know x bar, if we know x bar, the value of x bar, then knowing the sample, so if we know the average number of heads that happened in the sample, but after that we also came to know the sequence of heads, it does not add any extra information to P, the parameter. So you can say the sample is connected via this Tx to the parameter P. So what you can say? You can say that given Tx, the distribution of the sample of data given Tx, or sorry, the distribution of data given Tx is independent of P. So P is a real number here. So independent of P means it does not contain the value of P. The value of P or the expression P, since it's like a real number. Right? Makes sense? Super beautiful, right? Expression P. So the function, the distribution, the joint distribution of data x curl given Tx is independent of P. That is, does not contain the value of P when you write it down. Right? That's the definition, guys. That's how R. F. Fisher stumbled upon the sufficiency principle. And then it was mathematically modeled. So also another interesting thing is whatever the sample is, if it yields the same x bar, for example, you have 1 0 0, like if you have heads tails heads heads tails heads, and if you have heads 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 tails heads tails, both of the sample will have x bar 4/6, but the samples are different, so it's not adding any extra information. That's the beauty. That's the beauty of it. So the theta is dependent on via 2tx, via like the theta is dependent on the sample via tx. That's the best idea. That's what is meant by this. So if you ask me to write it down like properly, so you can say that both are dependent, both are giving same x bar is equal to 4/6, and it's dependent on through p bar. So essentially, this sample does not really matter. Only the x bar value matters. The question is that how to find this Tx, the next question. So in this module, we learned about the sufficiency. Today's week is all about sufficiency, this upcoming week. And we learn about what is sufficiency. We understood the history and philosophy of it. And we will give examples of it. And we'll see an algorithm to find sufficient statistic, which will use something called like Neyman factorization theorem. And it's a very interesting theorem. It gives an algorithm to find out it. And then we will do properties of sufficient statistics, whether it's unique, whether it's always exists. Of course, it always exists because we will see that someday in the next week. And we will also see that, we will see by definition of Neyman factorization theorem that sufficiency is closely related to MLE. Okay, and also we have made a video on that. I will link that in the corresponding this video. And it's closely related to the MLE. Okay, and we have an interesting idea of sufficiency principle, functions of another sufficient statistic. So the question is that, can we find the statistic function of sample which is sufficient, like which is sufficient for the parameter? And we'll see that like various properties of this, and we'll see minimal sufficiency, the minimum amount of minimum in what sense? We'll see that minimum in what sense. We want to see the minimum statistic, the minimum comparison that we can have for the parameter theta. And then we will move on to exponential family, and we'll discover something interesting about that, and it will be a beautiful set of lectures. I'm so excited for this. We are so excited for this, and the sufficiency principle is so important to the modern day, like in terms of data compression. And the idea is very beautiful. I hope you will enjoy the lectures, and I will see you in the classes. And all the best. Stay tuned. Bye bye. Also, if you have any questions, ask in the comments. If you want us to make some videos on, share in the comments. We will love to make on that. Thank you for your time. Thank you for watching. See you soon. Bye bye.